Hi everyone, we are back and we are on our problem 4, last problem, don't be a creep. So let's look at the deformation mechanism maps here. So let's label them so we know this is theoretical, 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 DG, dislocation glide, dislocation glide, dislocation glide. This is going to be power law creep or DLC, power law creep. This is going to be NH, this is going to be NH, this is going to be NH, Cobol, Cobol, and Cobol. Excellent. Rank the yield strength of the three maps. Yield strength is here, here, and here. So our yield strength for C is going to be greater than our yield strength for B, which is going to be greater than our yield strength for A. And we know that our grain size of A is going to be greater than our grain size of B, which is going to be greater than our grain size of C. Excellent. Maps A, B, and C are the orange, red, and black curves, but not necessarily in that order. Maps which match correlates with this material, rank grade size, dislocation density, concentration solute. What strength is occurring here? Okay, so because our Cobol creep region is changing, we know it's probably going to be either work hardening or grain size strengthening. So we know, what is it, orange, black, and red. So orange, black, and red. So we know that black is A. So that's going to be black, orange, and red. And we already ranked those values. One thing that we should be concerned here is that this should fail much shorter. They should have longer ductilities, but we'll ignore that for now. And describe the scaling parameters. Work hardening scales as dislocation density to the 1/2 power. This scales as dg to the -1. Excellent. Describe under what conditions Cobol creep, Navarro herring, and PLC will occur. So we know that Cobol creep scales, so our strain rate, scales as dg to the -3, and it scales as our, basically we're looking at the activation energy of the grain boundary diffusion, which is always faster, and that activation energy is always lower than for Navarro herring, which scales as dg to the -2, and that's the lattice bulk diffusion. PLC, dg to the 0, but it's stress to the 4 to the 6 power, and it's also lattice diffusion. So again, this will dominate at high stresses. This is going to dominate at lower temperatures and smaller grain sizes, and this will dominate at, again, higher temperatures than for Cobol creep, but much lower stresses than for PLC. And again, it can dominate even at larger grain sizes. Now, why doesn't Cobol creep always contribute more based on the fact that this diffusion is always larger than this diffusion? Well, it's because, again, the total amount. So if I have large grain sizes, there's not as many diffusive paths, so I can't, that contribution is going to be smaller for diffusion along that path. So that's going to be the rationale there. Add another curve of the stretching curve for the blue material that is now precipitate hardened. So if we're precipitate hardened, we may see a change in slope, so a higher Young's modulus and a higher yield strength, and then failure. That's precipitate hardened. How the curve changed, the volume fraction of the precipitate significantly increases. So if I have more precipitates, I'm going to see an even larger yield strength, and then an even shorter, basically even more brittle. And we know that if we increase our precipitates, we are going to be even more likely. So we're going to, our radius, so this is basically our cut regime versus our bow regime. So we want to bow around the larger particles, cut the smaller particles. So if this is our kind of normal curve, if we increase our precipitates, we're going to go like here and here. That's it. That is your practice exam. So we'll see you in the next video. Thanks. Bye.